Hello and welcome to this new segment of CD spectroscopy and Mossbauer spectroscopy for chemists. My name is Arnab Datta and I am an associate professor in the Department of Chemistry at IIT Bombay. So, in the previous segments we are discovering the different symmetry elements and operations present in the nature and having a mathematical perspective of these particular systems. And from there we figure it out that there are different groups can be formed with the different symmetry elements present. And out of these 5 symmetry elements that is present in a molecule, that could be present in a molecule, are identity operator, single axis of rotation, plane of reflection, improper axis of rotation and center of inversion. And all of them can be combined in a particular way to differentiate them in different 4 segments of the groups. And those we have defined how we can figure it out, and then we try to find out by asking rational question how I can easily figure it out what will be the point group of a molecule. So, in the last class we have done that. So, today we will just recap a little bit and then go through different examples of molecules and try to do this exercise to find out the point group of a molecule. So, let us begin. So, first of all again we are going to showcase that how to figure it out the point group of a molecule. So, you can say it is point group determination. So, what I am going to do, we are going to ask some question. The first question we are going to ask is the molecular structure that we are dealing with, is it linear or not? And the question will ask in such a way that it will be binary, either yes or no answer. If it is yes, the next question I am going to ask, do you have a center of symmetry or not? And again 2 possible answers, yes or no. If it is yes, then it belongs to the point group of D infinite H. If it is no, it belongs to the molecular point group of C infinite V. So, these are the things when you have a linear molecule. If the answer is no, if the molecule is not linear, the next question we ask whether they belongs to any particular cubic groups or not. And by this particular cubic group, by mean only 2 particular groups that is mostly common in chemistry, octahedral and tetrahedral. So, if the answer is yes, the molecule is not linear, but it belongs to particular point group which is easy to figure it out, then it belongs to this particular cubic groups. And most of the time we will find the molecules that we are dealing with is not that simple, it is not linear or neither it belongs to a particular cubic group, it will be much complex than that. And there we need to ask the next question, it is not linear, it is not cubic group, we will ask do you have a axis of rotation or not. If the answer is no, that means it belongs to a non-rotational group, then the next question we ask whether you have a center of symmetry or not. If the answer is yes, it belongs to Ci point group. If the answer is no, the next question we ask, do you have a sigma or not? If the answer is yes, this belongs to Cs point group. If it is no, then it is C1, the most simple of the molecule without any symmetry operation or element present other than the identity operator. And these 3 groups C1, Cs and Ci belongs to non-rotational group. But if the molecule has a Cn present, then we can be either in the single axis rotation group or dihedral group, and the factor that differentiate between them is this one. Do you have a number of C2 perpendicular to that principal axis Cn or not? If the answer is no, that means I belong to the Cn based point group, and over there then I figure it out whether they have sigma H or not. If yes, that will be CNH point group. If the answer is no, Then the next question we ask whether you have n number of sigma v's or not along with you. If the answer is yes, they belong to C and V point group. If the answer is no, then it belongs to Cn point group. So it does not have n number of C2s perpendicular to Cn, but it can have sigma h, so it is CnH, you can have sigma v's, it will be CnV, or nothing, it will be only Cn, and all this thing belongs to single axis rotation groups. And if it does have a number of C2 perpendicular to Cn, then the molecule belongs to Dn point group. So we go to, do you have a sigma h, the similar line of questioning that we have done just over here. We are just going to repeat it. Sigma h, if the answer is yes, the molecule belongs to DNH point group. If the answer is no, then we ask the question, do you have a number of sigma d's with you? Over here there are sigma d's because the presence of C2 is such that if the sigma v's are present over there, they will be bisecting those C2s. So that means they will be recognized as sigma d, and if it does have those sigma d's, that will belong to D and D point group, and if it does not have anything other than Cn and n number of C2 perpendicular Cn, that will come to a Dn point group. So with that we actually configure that these are the dihedral groups. So that we are went into in detail in the last segment. Now we are going to use them, how to do this questionnaire and figure it out, how we can figure it out the point group of a particular molecule. So we will take some examples. So the first example we are taking is the BF3 molecule. We have looked into this molecule earlier. It is actually a planar molecule. The plane of the molecule is drawn in such a way that it is perpendicular to the plane of the board I am drawing right now. And what is the point group of this molecule? So what we are going to do, start asking questions to this molecule. The first question we ask to the molecule, are you linear? And you can see obviously the answer is no. Then the question is, do you belong to any particular cubic groups? That means I am asking whether you have octahedral or tetrahedral geometry, and obviously from this geometry you can see it is no. Then comes, do you have a principal axis? And the answer is yes, there is a principal axis over here where you can rotate 120 degree and get to this molecule. So if I draw this molecule from top view motion, so this is the side view and this is the top view of the molecule, and you can see this molecule is done in such a way that over here through this boron, if I rotate 120 degree, I am going to get an indistinguishable and superimposable structure. So that means there is a C3 present over there, which is drawn over here in this particular side view molecule. So the answer is yes, and it has a C3. Now once you have a C3, now it belongs to either single axis rotation or dihedral group. To figure it out whether it is dihedral or not, next question I will be asking, do you have 3C2 perpendicular to your C3? So it is n number of C2 perpendicular to your Cn, so n is 3 over here. So I am asking, do you have 3C2 which is perpendicular to C3? So you can see over here, along with each BF bond I have a C2, I can rotate 180 degree and I am going to get a similar structure, indistinguishable and superimposable, because this BF bond is remaining same, the other fluorines exchange places. See in this structure from the top view over here. It is not only over here, it can belong to any of the C2 belongs to the BF bond. So as I have told earlier, if a molecule have a perpendicular C2 compared to its principal axis, either you will have n number of it, n is the Cn axis of this principal axis, or none. So once you find one of them, obviously you see in a symmetric way you can find the other also. So I found one C2, so there will be other two C2, so you can have 3 C2 perpendicular to C3. So the answer is yes. The next question we ask, whether it has a sigma h or not. Sigma h means principal axis is this C3, a plane perpendicular to it, and you can see all the atoms belongs to that plane. So, that means it will be a mirror image on this particular plane reflection, which will be exactly sitting on the top of the original molecule. So, that means it is a sigma and it is a sigma h. So, the next question you ask whether you have a sigma h or not, answer is yes, and this is nothing but from the top view molecule is the plane of the board, and in this particular system is the plane perpendicular to the board, and you can see the answer is yes. So, the molecular point group for this molecule will be D3H, that we can figure it out from here. So, that is how we actually figure it out, all these particular molecules. The next question, let us do ammonia. This is the structure of ammonia. The lone pairs. So, it is a trigonal pyramidal structure. Now, we try to find out what is the point group. Again same line of questioning. Is this molecule linear? Obviously not. Is this molecule belong to any cubic group? So, some of you might need to say yes, might think about saying yes, because it is having a tetrahedral structure. Yes, it may have a tetrahedral geometry around it, but it does not have all the same ligands all places, because this is a lone pair over here. So, that actually breaks the tetrahedral symmetry, and it is not a tetrahedral geometry. So, it does not belong to any cubic group. Next question is what is the CN, and the CN is actually this nitrogen, where you are having a C3 axis of rotation. You can see nitrogen remain as it is, all the other hydrogen changes places. So, yes, the CN is present and it is C3 axis. And the next question is, do you have sigma H? So, if sigma H has to be there, it has to be through the center molecule and will be perpendicular to it, and you can see it is not a plane of reflection because the nitrogen remain as it is, but these 3 hydrogen will come on the top of this plane, which is not the superimposable and indistinguishable structure. So, that is why this molecule does not belong as sigma H. Then the next question is, do you have 3 sigma V's? So, just drawing the structure one more time. So, you can see this particular plane, the plane of the board containing this NH bond is going to remain same. These hydrogens will replace with each other. So, superimposable and indistinguishable structure, and that is going to happen in 3 different planes belong to each of the NH bond. So, that will be sigma V plane, because that actually contains, each of them contains the principal axis C3. So, that is why they are all 3 sigma V's, and yes, it is present. So, this point group of this molecule will be C3V. So, that is the 2 examples we have gone so far. Now, we are going to move a little bit more after BF3 and ammonia. We go to the next set of example. The next set of example I am going to do is N2F2. What is the structure of the molecule? And that is the interesting thing. This molecule can have 2 different structures. This is the nitrogen double bond, and then you can have 2 different orientations of the fluorines. Either they can be in the same side, so that is known as the cis geometry. So, let us take it is a cis. So, this is the cis geometry structure. And what is the other structure possible? So, it is possible that this molecule is such that these fluorines are in opposite inside. So, that is the trans molecule. So, we will try to find out the point group of each molecule one by one. First, let us go to the cis. Again, questionnaire is very much similar. Are you linear? Question is, answer is no. Next question is, do you belong to any cubic group? Answer is no. what is the Cn present in this molecule? Just when you look into it, you can find there is a C2 present over here. If you rotate 180 degree, the nitrogen and oxygen bonds exchange places, the fluorines exchange places, but you are going to get a superimposable and indistinguishable form. So that means a C2 is present is yes, it is C2. Next question, do you have two C2 perpendicular to that C2? So that means somewhere around here or somewhere around here, and those are not having any C2s, because if you rotate over here you can see that nitrogen is remaining same, that the fluorines come on the top side from the bottom. So that is not going to match the original configuration. So there is no. So that means it does not belong to a dihedral group. Next question, do you have a sigma H? So if it has a sigma H, it has to be in this particular plane perpendicular to this C2. And the answer is no, it does not have a sigma H, because these two fluorines are again going to change its place if we do this operation. Next question is, do you have two sigma V's? So now over here you can see this plane perpendicular to this plane of the drawing and the plane of the molecule itself. The plane of the molecule contains all the atoms, so the reflection will be exactly on the same place. So that is a sigma V for sure, because it contains the C2 also, and this one perpendicular to is actually bisects each another and all of them goes to their respective places. So that is also sigma V. So these are the two sigma V's present over there, answer is yes. So this molecule belongs to C2V point group for this cis molecule. Now the trans molecule. Of the trans molecule, we are starting to do the same question, whether you are linear or not. The answer is no. Cubic group, answer is no. Do you have a Cn? Now previously our Cn was somewhere around here. Now if you rotate that, the fluorine will come to this side, this fluorine will go to this side, so they are not really matching to this original position with 180 rotation. But what happens if I rotate over here? This is the plane of the molecule perpendicular to it, and if you rotate 180 degree, the nitrogens remain in a similar position, but this nitrogen comes from the left to right and right to left, and over there the nitrogens are remaining in the same place. Similar thing happens to the fluorine with 180 degree rotation through this axis over here, which is perpendicular to the plane of this molecule. What we are going to get, this fluorine is going to come over here and this particular fluorine is going to go over there. So that means it remains as it is. So that means there is actually a C2 present over here. So answer is yes, and it is a C2. Now the next question, do you have two C2 perpendicular to that C2? That means somewhere around here or somewhere around here. So none of them rotate 180 degree and give you a same structure. This rotation over here, the fluorine will come to left to right, right to left, not on the top of each other. Same thing over here, if you rotate from there, bottom to the top, top to the bottom, but not really on top of each other. So the answer is no. Next question, do you have a sigma H? Now sigma H is now the plane of the molecule, because your principal axis of C2 is now perpendicular to it. So if I draw this molecule like this, this is the plane of the molecular thinking, and this is where the C2 is. So you can see C2 is actually perpendicular to the plane of the molecule, and which is actually containing all the atoms over there. So it is a sigma plane, but because it is perpendicular to it, it is sigma H. So answer is yes, it has a sigma H, and point group will be C2H. So please take a look into it one more time at your favorable condition and find out whether it is actually making sense to you. Cis C2V, trans C2H. Now the next one, we are going to do with XCF4 molecule. So how does this XCF4 looks like? So again we are going to draw two different orientation. One is from the side view, this one, and one is from the top view. So, this is the plane of the molecule. So, now when we look into that, we start asking the same question, are you linear or not? Answer is no. Cubic group, answer is no. You have a CN, the answer is yes, and it is actually having a C4. Directly go through xenon. If you rotate 90 degree, all the fluorine exchange places, but goes to a similar looking orientation where the xenon is not even changing its position. So, it actually have a C4. So, over here C4, so these are the 90 degree angles. So, once that sorted out that I have a C4, now the next question is whether it belongs to deep hydral group or not. So, do you have 4 C2s perpendicular to C4? So, over here you can see we have gone through that earlier also. 2 sets of C2s will be there which will be going through the fluorine xenon fluorine bond. Whereas the other 2 will be going through the xenon fluorine xenon bond, fluorine xenon fluorine bond. There is other C2 and there is a other C2. So, all together you have 1, 2, 3 and 4 C2 present. Answer is yes, it belongs to dihedral group. Then it is a sigma H or not. Sigma H will be a plane perpendicular to the principal axis, which is the molecular plane. In the molecular plane we already have 4 fluorines and xenon sitting over there. So, even if you reflect them, each and every of them is reflecting onto each other. So, it is symmetric molecule and it is going to give you a similar configuration from the original one. So, sigma H, the answer is yes. So, the point group of the molecule is D4H. So, that is the point group of this molecule. The next one we are going to do is the following. Is a cobalt molecule with 5 ammonia, 1 chloride, and the overall structure charge is +1 because it is a cobalt 2 system. Now, looking into that, you can see there are 5 ammonia, 1 chloride ligands. So, the geometry is going to be octahedral because that is the geometry the metals preferred in biology. So, now I am putting ammonias over here all around the place. And 1 chlorine over there. And over here what you can see that this molecule obviously not linear, but does it belong to a cubic group? Because this molecule is an octahedral symmetric structure it has. But over here you have to understand this, although it looks like octahedral coordination geometry, the symmetry is not octahedral. Because to have a symmetry octahedral, you have to have all the 6 ligands connected to the central atom same. So, over there are 5 ammonias, but one of them is chlorine, which is dissimilar, and that actually breaks the overall symmetry. The coordination geometry is octahedral, no problem with that, but the symmetry is not octahedral. So, you have to understand the difference between coordination geometry and absolute symmetry. Coordination geometry is like how they are actually interacting with the all ligands and how the bonding direction coming from the central atom. But the symmetry defines what are the identity even for the atoms connected to the central atom, and with respect to that it is not an octahedral. So, it does not belong to any cubic group. Then comes what is the principal axis of this molecule. So, principal axis of this molecule belongs to this when it is going through chloride, cobalt, ammonia system, and it is having a C4 axis over there, 90 degree rotation. If I try to take a look from the top view of this molecule, I am going to see a cobalt over here and all ammonia sitting what it is called the equatorial plane, and this axial position has chloride, also has an ammonia at the bottom, but they all belong to this one particular line. So, now if I rotate C4 along with this line, that means over here the chloride, cobalt and ammonia does not change the position, the ammonia in the equatorial plane change the position, and that is actually making sure that I have a C4 axis. Next question is, do I have force C2 perpendicular to the C4 or not? If it has to have 4 C2s, it will be somewhere around here or here. And you can see if you rotate it, the ammonia and the cobalt, ammonia present in the equatorial plane is remaining as it is, the cobalt is remaining as it is, but this chloride and ammonia present in the axial position, they will be changing its position, and that will be not superimposable and indistinguishable from the original structure. So that is why we can say it does not have force C2 perpendicular to this C4. Then the next question, does it have any sigma h? Sigma h again will be the equatorial plane, because that is the only plane perpendicular to that C4. All the ammonia in the equatorial and cobalt is going to be as it is if I do a sigma operation around this particular plane, but this chloride and ammonia will exchange places, and again it is breaking the symmetry. So you can say there is no sigma h. Then the next question comes, do you have 4 sigma v's then? And that answer is yes, because those are actually present along with this equatorial ammonia cobalt ammonia bond. So for an example, like this particular plane is one of them, and it actually contains ammonia, chloride and ammonia in the axial position onto it, the C4, and these 2 ammonia is going to reflect it. Same thing happens when I am going through this particular way. So there is one sigma v, this is a sigma v. We can have sigma v's going between the ammonia cobalt ammonia bond. So altogether 4. So for an example, over here the plane of the board I draw in this side view, it is actually going to be one of the sigma v planes. So I have 4 sigma v planes, 2 of them goes through the bonds ammonia cobalt ammonia in the equatorial plane, and 2 of them will go between those 2 bonds. So answer is yes, I have 4 sigma v's, and this will be C4V molecule in the point group. Now I go to the next one, which is I am drawing an alkene type molecule, hydrogen, hydrogen in the cis position, and the rest of them is a chloride and a bromide. So what is the point group of this particular molecule? So this ethylene derivative has the same question, are you linear? Answer is obviously no. Do you belong to any cubic group? Answer is no. Then the next question comes, do you have an axis of rotation Cn? And here is this thing, if it is axis of rotation, it can be either in this particular system. If you rotate, you can see bromine and hydrogen changing places. Over here hydrogens are remaining as it is, but the chlorine and bromine takes places, so no axis of rotation over there. One is perpendicular to this board, again the hydrogen and hydrogen is actually changing places, because this hydrogen will come to opposite trans, this hydrogen goes to the opposite bromide, so that is also not working. So altogether this molecule does not have any Cn axis of rotation. Then comes, does it have a center of symmetry? Center of symmetry has to be in the center of molecule, and you can see this chlorine versus hydrogen, chlorine versus bromide. So obviously no I. Does it have a sigma plane? So that sigma plane is the plane of the molecule, because this is a planar molecule, alkene molecule, and this molecule is actually planar, and that contains all the atom on its place. So if you do a mirror image, all of them actually mirroring on each other's original position. So that is why it contains a sigma plane. And over there, as we asked, there is no Cn axis present over there. I cannot differentiate the sigma as a sigma h, sigma v or sigma d, because there is no Cn axis present. So that is why it remains as only sigma, and the point group of this molecule is Cs. That is the point group of this molecule. We will go to the next one, number 8, which we are actually doing a alkane kind of molecule. There I have a chlorine, I have a fluorine on the back, hydrogen on the front, and then hydrogen on the back, fluorine over here, and chlorine over here. So, this is an alkane based molecule over here, and we try to find out which is the point group of that. So, one of the other way to look into this molecule better is the Newman projection. And how that we do, we draw, say I am looking from this particular direction to this molecule, and over there I am going to see one dot is the front carbon, that is having a chloride on the top, fluoride on the left, hydrogen on the right hand side if I am looking from this particular direction. And on the back carbon I will draw as a circle, and over there chlorine is over here, fluorine is over here, hydrogen is over here. So, that is the Newman projection of the same molecule. So, these are the same molecule. Now, over here I am going to ask the same questions. Are you linear? Answer is no. Next question, do you belong to a QB group? The answer is still no. Do you have a CN axis of rotation? So, over here you can try to find different axis of rotation from here or even perpendicular to that, and you can see whatever the rotation you are going to do, you are not going to get any new configuration which matches to the original. So, that means this molecule does not have an axis of rotation present in this molecule. Next question, does it have a sigma plane? So, you can see the sigma plane, we can have it along this plane of the board, and you can say like it is nothing but this plane over here in the Newman projection. You can see chlorine, carbon, chlorine remain same, but hydrogen and fluorine will be replacing space. Similar case over here, that is actually not going to work, and the similar question is that plane of the board perpendicular to it if I take a sigma plane. So, that is also not working. So, any particular plane is actually not going to be working. So, there is no sigma. Now, the question is, does it have a center of inversion? It has to be in the middle over here if it is there. So, this hydrogen passes through that. Is it reaching to a hydrogen? So, it is easy to see from this Newman projection, hydrogen going through that center of symmetry, the midpoint between the carbon-carbon bond, you can reach a hydrogen. Fluorine reaches a fluorine, chlorine reaches a chlorine. So, that is how it is going through, and over there it retains its center of inversion, and carbon-carbon obviously is doing the reflection. So, that means yes, it has a center of inversion, and the point group will be Ci. So, I would suggest you to take a look into this molecule on its own and try to visualize it, and then you can do it properly, that yes, there is a center of inversion at the midpoint between CC bond. So, with that we go to our next example, which is actually a ethane molecule present in its eclipsed configuration. So, as we know, the ethane molecule can be present in this kind of configuration. This is known as the eclipse configuration, which is understood better if I draw the Newman projection of it. So, the front carbon, hydrogen on the top, hydrogen on the left, hydrogen on the right, the back carbon as a circle, this is the hydrogen over there almost on top of each other. We are drawing a little bit moved over there so that we can see it properly. So, that is how it is happening. So, almost on top of each other. What is the symmetry of point group of this molecule? So, the question you are going to ask, are you linear? Answer is no. Are you cubic group, tetrahedral or octahedral? Answer is no. Then comes the question, what is the CN axis of this molecule? And the CN axis is actually present over here along with the CC axis. If you rotate 120 degree, so over here 120 degree, this hydrogen comes over there, this go there, this go there. So, similar, and same thing happens on the back side carbon also. So, that is why yes, a CN axis is present, it is a C3. Next question, do you have 3 C2 perpendicular to that C3, so that we can differentiate between dihedral and single axis rotation group. So, does it have any C2 perpendicular to C3? So, for that what we need to take a look into it is that where it is possible. So, the C2 is actually present over here where? So, it is actually going through the CC bond and through this over here, one over here and the other one over here. So, basically one example over here going through this hydrogen carbon hydrogen, middle of that over here. If you rotate 180 degree, this hydrogen comes over here, this hydrogen comes over here, and the rest of them also changing its place because all of them are hydrogen. So, they are remaining as it is, carbon carbon also position changes, but the overall final configuration you are going to see will be similar to the original configuration. So, there is a C2 over here and the similar C2 present also along with the other hydrogen hydrogen bonds, the other one from there, which is seen better if we look through this particular structure between the hydrogen carbon hydrogen bond and through this carbon carbon bond there is a 3 C2s present, and obviously all of them you can see is perpendicular to that original principal axis C3. So, now the next question is, do you have a sigma H? Sigma H has to be the perpendicular to the principal axis. So, in this molecule is a plane on the top Newman projection. Is a plane, and over there it is the perpendicular plane to the board of the board, and over here you can say yes, the sigma H is present because all of them are reflecting on its own, hydrogen to hydrogen, carbon to carbon. So, it is present. The molecular point group of this molecule will be D3H because it has a C3, it has 3 C2 perpendicular to C3 and also a sigma H. Now, the last example of this system is cyclohexane, and we are going to draw the chair form of it, and we try to find out what is the point group of this molecule. That is how the chair form looks like. And these are all the position of where the hydrogens will come into. So, this is the molecular structure. We have to find out the point group of it. So, first question is it linear? Answer is no. Next question, whether it belongs to any particular cubic group? Answer is still no. Then the question is, what is the principal axis or CN? That is actually going through this molecular structure through the middle, and it has a C3, but it is not very easy to see it from here. So, what I am going to do, I am going to draw a structure of a cyclohexane in this kind of way, top view. If I look it from the top over here, you can see 3 of them is actually above the plane and 3 of them is bottom the plane. So, the top ones I am actually drawing as positive. It is not a positive charge or anything, just to showcase that it is above the plane, and 3 of them as negative, again not a charge but to showcase they are below the plane. So, over here positive means above the plane and negative means below the plane. And now, if you rotate it from here 120 degree, so this is 60, this is 120, this 60, 120, 60, 120. You can see the above the plane carbons reaches to the above the plane condition, and similarly this is also going to get to the below the plane system. So, they are remaining as it is. So, there means there is a C3 present over here. So, yes, this is present, you have a C3. Next question, do you have 3C2 perpendicular to that C3? That is the question we have. So, that means where it can have been. So, it is possible to have it if it is going through here. So, it is better to see it from here. See, if we rotate 180 degree over here, you can see if we rotate 180 degree, this bottom one present over here, 180 degree rotation, it will go to the top will come to the bottom. So, this negative will go to the positive, positive will come to the negative. This above the plane will go to the below the plane will come above the plane, similar over here. So, there is a C2 present over here, which is bisecting the CC bond, and there are 3 possibilities, because as we said, if you find one of them, other 2 will be also there, because either it will have 3 of them or none, and it will be very similar position going through the C3 perpendicular to the C3 axis, the principal axis, and going through the CC bond. So, yes, this molecule is having the 3 C2s. Next question, does it have a sigma H? Sigma H has to be the plane of this, because it will be the perpendicular plane, and over here when you do that, you can see the plane is actually perpendicular to this principal axis, but this above one will go to the down, down will come to the bottom above. So, this plus and minus signature will be changing, because they are not on the plane of this sigma. This is above or below, plus belongs to above, negative belongs to below, and they will change their position. So, that is why there is actually no sigma H present. Then the question, do you have sigma V's present? So, for the sigma V's, what we can see over here, there is a sigma V plane present. So, let me just draw that in a different color to showcase it properly. So, here is the sigma V plane present. Why it is a sigma V plane? Because over here you can see the negative and the positive that I shown over here, which is belongs to this plane, the above and below one will return to the plane. This positive side will be reflecting, this negative side will be reflecting. So, the top remains on the top, bottom remains on the bottom, everything remains same. So, the sigma V plane is actually going through this carbon atom, not through the bond as C2. That means there will be another one coming over here, sigma V, and another one going through this one. And you can see each sigma V is bisecting the C2s, right. This particular C2 and this particular C2, you can see it is bisected by this sigma V. Similarly, this C2 and this C2 and this C2 is bisecting this, and this one and this one is bisecting this one. So, yes, it is present and it is nothing but sigma D's. So, that means it will be a D and D or D3D point group in the structure. So, that is how we differentiate the different molecules with respect to the point group, and that is how we figure it out the point group of different molecules. So, with respect to that, we would like to conclude over here, and we hope now we have a very good exercise how to find a point group and how to ask this question and figure it out. So, we would like to request you to follow the question that will be coming in the assignment and do it, and if you have any issues on the visualization, try to draw that in different orientation that fits your imagination better, and try to resolve what is the point group of the molecule. With that, we would like to conclude this particular exercise session over here, and we look forward to discuss further on the chirality and its connection to the point group. Thank you very much.